All right, welcome everyone to another deep dive. Today we're tackling something that's, well, it's kind of a hidden gem. It's like the secret sauce that makes your computer actually tick.
It is. It is, really. And
Yeah.
most people, they don't even realize it's there.
Right, but without it, chaos. Total
Pretty
chaos.
much. You'd be stuck in the digital dark ages.
We're talking about the Enhanced Configuration Access Mechanism, or as the cool kids call it, ECAM, and it's all happening within the world of PCI Express, or PCIe.
Yeah, PCIe, that superhighway of data inside your computer.
We all know about PCIe. It's what makes your graphics card, your network card, all those goodies talk to each other and to the CPU, the brain of the operation.
And ECAM.
Yeah.
Well, think of it as the traffic cop, the air traffic controller for all that data whizzing around.
Love that analogy. So for this deep dive, we've gone through a bunch of stuff, technical documents, those dense things, but also industry glossaries because, let's face it, sometimes you need a decoder ring for all the jargon.
Absolutely.
Yeah.
And even some forum discussions online where the real enthusiasts hang out.
Right, where the deep cuts happen. And the mission here is to really get a grip on this ECAM thing. Why it matters, how it works, all of that.
Yeah, because when you understand ECAM, you understand a fundamental piece of how modern computers really work.
And it's not just about being a tech whiz. ECAM is what makes plug and play possible. You buy a new graphics card, pop it in, and boom, it works.
Right. No need to mess with jumpers or dip switches like in the old days.
The dark ages.
Yeah. ECAM allows your computer to automatically identify and configure new hardware.
Magic, right. But sophisticated magic, we're going to find out how.
So let's talk about what ECAM actually does. In a nutshell, it lets software, like the firmware when you first boot up your computer and then later the operating system, talk to all the devices connected via PCIe.
So it's like a universal translator.
Kind of, yeah. Because each device has this thing called a configuration space. It's basically a little profile that tells the computer everything it needs to know about that device.
So the device is like, hey, I'm a graphics card made by so-and-so, and I need this much memory and these kinds of connection.
Exactly. And ECAM is the way the computer reads and writes to that configuration space.
Okay, so that's how the computer knows what each device is and what it needs. But how does that translate to plug and play?
Well, because of ECAM, when you plug in a new device, the operating system can automatically read that device's configuration space.
So it's like the device is introducing itself.
Right, and the operating system is like, okay, I see what you are and I see what you need. Let me set things up for you. And boom, your new hardware is ready to go.
Pretty slick.
Okay.
But it's not just for initial setup, right?
No, not at all. ECAM is constantly being used, even when you're just using your computer normally.
So like when I'm browsing the web or editing a video or something.
Exactly. Think about it. Every time your computer needs to communicate with a PCIe device, it has to use ECAM to access that device's configuration space.
Okay, that makes sense. And I guess that's why it's so important to understand this stuff. It's happening all the time, even if we don't see it.
You got it. So let's break down how ECAM actually works. Now, this gets a bit technical, but stick with me.
I'm ready. Hit me with it.
All right. So remember how we talked about each PCIe device having a configuration space? Well, ECAM uses something called memory mapped access to get to those spaces.
Memory mapped. Does that mean the configuration spaces are actually stored in the computer's memory?
In a way, yeah. It's like this. A specific chunk of physical memory is set aside just for PCIe configuration, often something like 256 megabytes per segment.
Whoa, that's a lot of memory for just configuration.
It sounds like a lot, but you got to realize that modern systems have a ton of PCI devices, and each device needs its own space for all those configuration settings.
So this dedicated memory region is like a giant map, and each device gets its own little plot of land on that map.
That's a great way to think about it. And each address within this memory region corresponds to a specific register within a specific device's configuration space.
Okay, I'm following so far. So if the computer wants to read a particular setting on my graphics card, for example, it goes to a specific memory address.
You got it. And that address is constructed in a very specific way. It includes the bus number of the PCIe device, the device number, the function number, and the offset of the particular register within that device's 4KB configuration space.
Wait, function number? What's that about?
Oh, right. Some devices, especially more complex ones, can actually act as multiple logical devices. Each of those logical devices is called a function.
Okay, so it's like One physical card can pretend to be several different devices.
Right, like a multi-talented actor playing different roles.
Gotcha. So the address tells the computer exactly where to find the specific piece of information it's looking for.
Precisely. And then the root complex, which is usually part of the CPU, takes that memory address and translates it into an actual PCIe configuration transaction.
So it's like the root complex is the interpreter.
Yeah, it's the one that speaks both memory address and PCIe command. It takes the memory address, figures out which device and which register it needs to talk to, and then sends the appropriate command over the PCIe bus.
And that command could be either a read command or a write command, right?
Exactly. If it's a read command, the device sends back the data stored in the requested register. If it's a write command, the device updates the register with the new data.
So it's a two-way communication channel.
Absolutely. And it all happens through this clever memory mapped mechanism.
Okay, that makes sense.
Yeah.
But how does the operating system even know where this dedicated ECAM memory region is located in the first place?
Good question. It's not like it's hard-coded into every computer.
Right, because every computer could have a different memory layout.
Exactly. So the operating system gets this information from the system's firmware, specifically through something called the MCFG table.
MCFG, another acronym.
Yeah, well, it stands for Memory Mapped Configuration. This table basically tells the operating system, hey, the PCIe configuration space starts at this memory address.
So it's like a signpost pointing the operating system in the right direction.
Exactly. And that's how the operating system can reliably find and use ECAM on any compliant computer.
Pretty ingenious, really.
Yeah.
But what about older systems? Did they use ECAM too?
Not quite. They used something called configuration mechanism #1, which relied on specific I/O ports to access the configuration space.
I/O ports, like the physical ports on the back of your computer?
A similar idea, but these are internal ports. And the biggest problem with this older method is that it can only access a very limited portion of the configuration space, only the first 256 bytes.
256 bytes, that's tiny.
Yeah, especially compared to the full 4 KB that ECAM can access.
So ECAM is a huge step forward in terms of giving us access to all those configuration options.
Absolutely. And it's essential for supporting all the advanced features of modern PCIe devices, things like complex power management, high-speed data transfer, and error correction.
And I guess with the ever-increasing complexity of hardware, having that extra configuration space is more important than ever.
Absolutely. Plus, legacy PCI was limited to a maximum of 256 buses within a system. ECAM, on the other hand, supports extended PCI bus numbering, which means you can have way more devices connected.
So it's not just about more configuration options per device, it's also about being able to connect more devices in the first place.
Right, which is crucial for things like servers and high-performance workstations.
Okay, so we've talked about how ECAM works and why it's important, but I'm curious about those base address registers, or bars, that we mentioned earlier. How do they fit into all of this?
Ah, BRs. They're like the device's way of requesting resources from the system.
Resources like memory and I/O space.
Exactly. Each bar specifies a range of addresses that the device needs to operate.
So it's like the device is saying, I need this much space to store my data and handle my inputs and outputs.
Right. And during device initialization, the system uses ECAM to read the bars and figure out how much space each device needs.
So it's like taking inventory of all the requests.
Exactly. And then the system has to decide how to allocate those resources. It has to make sure that each device gets the space it needs without overlapping with other devices.
That sounds like a tricky job.
It can be, especially in a complex system with lots of devices. But once the system has figured out the resource allocation, it uses ECAM again, this time, to write the assigned addresses back into the device's BRs.
So it's like the system is saying, okay, you can have this chunk of memory starting at this address.
Precisely. And this establishes the mapping between the device's internal address space and the system's overall address space.
So now the CPU knows exactly where to find the device's memory.
And it can communicate with the device directly using techniques like DMA, direct memory access.
Ah, DMA, that's what allows for those super fast data transfers, right?
You got it. DMA lets the device access system memory directly without needing to go through the CPU for every single transfer.
So it's like a high-speed bypass lane.
Exactly. And it all starts with those bars being configured correctly through ECAM.
Okay, this is all starting to click now. But are there any drawbacks to ECAM? It seems like such an elegant solution.
Well, no system is perfect. One thing to keep in mind is that while ECAM is great for configuration, it's not really designed for high bandwidth data transfers.
You mean like transferring large files or streaming video?
Right. ECAM access is relatively slow compared to the dedicated data paths that are set up through the bars.
So it's more about setting things up than moving lots of data around.
Exactly. And another potential issue is the fixed 4KB size of the configuration space per function. For really complex devices, that might not be enough space in the future.
So it's possible that we'll hit a limit at some point.
It's not impossible. And of course, implementing ECAM correctly can be tricky. You have to make sure the memory region is allocated correctly, and you have to handle all the address decoding and routing.
Sounds like a headache for system designers.
It can be, but the benefits definitely outweigh the challenges.
So overall, ECAM is a pretty amazing piece of technology.
It is. It's one of those foundational innovations that makes modern computing possible.
And it's a testament to the ingenuity of the engineers who designed it.
Absolutely. It's a system that works quietly in the background, enabling all the amazing things we can do with our computers today.
Well, that was a fascinating deep dive into the world of ECAM. I feel like I've learned a ton.
Me too. It's always fun to explore the hidden workings of the technology we use every day.
And it's a reminder that there's so much more to our computers than meets the eye.
Absolutely. It's a whole universe of complexity and innovation just waiting to be discovered.
Thanks for joining us on this journey into the heart of PCIe. We'll see you next time for another deep dive.
And now, a final thought to ponder. Think about how this seemingly obscure mechanism, ECAM, silently shapes the performance and capabilities of every device inside your computer. From the breathtaking visuals of your favorite games to the lightning-fast response of your SSD, ECAM plays a crucial role. So as technology continues to evolve, what might the future hold for this fundamental aspect of computer architecture? Could it be further refined, or might it eventually be replaced by something even more revolutionary? We encourage you to keep exploring the ever-evolving landscape of computer technology and to never stop asking questions about the systems that power our digital world.